Hello, everybody. So sorry that we have to do this over a pre-recorded video, but this is going to be the format that we do it for today because I'm really not feeling too well. So hopefully I can get through this and get you the information you need. So I'm going to break this into 3 different parts and upload them separately, but let's begin. So, when we're using chemical equations, we can understand quite a bit from what it gives us. So, we need to understand the molecular and mass information in a balanced equation. And there isn't a ton of mass information that you get out of a balanced equation, but there is plenty of molecular information, especially when it has to do with ratios of one element to another or one molecule to another. And this is where we use the coefficients that we have in the balanced equations that we've used before. And so in order to understand the information that we get out of a balanced equation, we need to take a look at one. This equation that's given here is indeed balanced with a 1 to 3 to 2 to 3 ratio. We could write this out in words to say that a molecule of ethanol, which is this compound right here, molecule of ethanol is going to react with 3 molecules of oxygen to produce 2 molecules of CO2 and 3 molecules of water. We could also say that this is moles, because if we were to convert moles to molecules, it would be doing the same calculation for each different element, and so we can look at this as molecules or moles. Either way is fine. So, if we have this, the following reaction represents the key steps in the production of pure copper from copper ores. We have this copper sulfide and copper oxide together to get copper and SO2 out. Now, what we would need to do first is balance it. So let's go back and begin to balance it. We have 2 coppers, so that's a total of 4 coppers, so we're probably going to need a 4 right there. We have 1 sulfur and 1 oxygen, but we need 1 sulfur and 2 oxygens. So instead, what I will do is I will double the number of copper oxides I have. That is going to change the amount of coppers that I have on the right-hand side, but it will correct the amount of coppers of oxygens that I have on the right-hand side. So now that we have 4 coppers and 2 coppers, we're going to add those together to make a 6 right there. Okay. So this is our balanced equation. It's a 1 to 2 to 6 ratio present there. And so, once we balance the reaction, the question is asking us to determine how many dozens of the copper atoms we can produce from a dozen molecules of the sulfide and 2 dozen molecules of the oxide of copper. So how many molecules can we produce from a dozen? Well, we know that a dozen is 12, and 2 dozen molecules of the oxide, copper oxide, is going to be 24. And so we will keep that in mind and answer the first part of this question. So how many moles of copper can be produced from 1 mole of the sulfide and 2 moles of the oxide? Okay. And so this next part of the question is basically the same, because it's saying 1 mole of sulfide and 2 moles of the oxide. Now, before we had 2 dozen molecules of the copper and of the oxide and 1 dozen of the sulfide. Cu2S and Cu2O and Cu2S. And this is saying the same thing. We have basically like saying 2 Cu2O and 1 Cu2S. And the reason I say they're the same is because the ratio of this to this is the same as the ratio of this to this. So we could divide all of these, all of the ones above by 12 to get the same number. But let's head back real quick. So we know that we have 24 dozen copper oxides. So let's start there. We have 24 dozen copper oxide. We have 12 dozen copper sulfides. Oh my god. Okay, and so what we can go back to is we know that this is how many atoms we have, but we don't exactly care about that. We're just looking at how many dozen we have. So from a dozen of the sulfide, that would mean that we have 1 dozen Cu2S. And so what we're going to do is we need to find out the number of copper atoms we have, or the number of dozens of copper atoms we have. For every 1 dozen, because there's an invisible 1 right there, there's going to be 6 dozen copper atoms that we get out the other side. So for every 1 dozen, we'll say 1 dozen Cu2S gives us 6 dozen Cu, and this is going to end up giving us a value of 6 dozen Cu. So just for clarity, all we did was we took the value that we were given, we used a conversion factor, and that was based on the values in the balanced equation. For every 1 Cus, whether that is a mole, a dozen, or whatever, there are 6 Cus that are produced from this. And so we can answer this just like this. So it doesn't matter if we start with one or the other, because we need one, in order to get 6 dozen Cus, we will need 1 Cus, 1 dozen Cu2Ss. And the other thing is that for 2 dozen oxides of copper 1, so that would be 2 dozen Cu2Os, we would also get out 6 Cus's. So 6 dozen Cus's. Cus, my bad. And so we could do the exact same math, and we would say that 2 Cu2O goes to, using the stoichiometry there, that would be 2 Cu2Os for every 6 Cus. So CuO and CuO get canceled out, and 2 and 2 get canceled out. The only value left is just 6 Cu. So 6 Cu is what we get out the other side. Now this could be dozens. This could be moles. What have you. It could be anything that, any kind of unit that is going to collectively just count the number of atoms. And so our answer ends up being this. 6 dozens, and 6 moles. And so this is our introduction to mole relationships. When we're looking at an equation, we have the ratios of each of the atoms, and from that we can see how everything works out. What is important is to note that when you balance an equation, you are always going to have the same ratio. So for example, if you have two H2Os that break down, these are always going to make two H2s and one O2. If you have four H2Os that break down, you'll get out four H2s and two O2s. But divide all of those values by 2, and you end up getting the same thing that was up there, 2, 2, 1. So mole ratios are what allows us to convert from moles of one substance in a balanced equation to moles of a second substance in the equation. So we can convert from H2O to H2 using the equation itself and using the numbers that go along with it. All right, so for this equation right here, we have Na2SiF6. We have 4 NAs going to Si and 6 NaFs. We want to know how many moles of NaF will be produced if 3.5 moles of Na is reacted with excess Na2SiF6. Now this excess business we'll get into later, why that's important. But for now, let's just take a look at what we're doing. So the first thing you should ask yourself when you are doing these problems is where you're going and what you start with. Where you're going is going to be the value that you want to determine. That's going to be both the number that you want, it's going to be both the number that you want and the unit that you want in the correct type of molecule. So NaF is part of this molecular equation, so it will be part of our answer. And we want to know when we have the amounts that we start with. So we need to balance. The equation is already balanced, so we don't need to do that. But we do know that we start with 3.50 moles of Na. Now, I think it's easiest to think of the numbers right here on the sides as moles. That's going to be the easiest way. You could also think of them as molecules, but moles is going to save you some time. So this is how we get there. We're going to start with the value that we begin with. The 3.50 moles of Na, that's what we have in our hand. The equation shows that for every 4 moles of Na, there are 6 moles of NaF that are produced. So our ratio is going to be 6/4. We're going to put the Na on the bottom to cancel it out. Then we will multiply 3.50 times 6 divided by 4. That ends up with this value right there, 5.25 moles. Okay, go ahead and try this out, and then we will come together and I will, well, actually this is the answer right here. Or this is the way to get to the answer right here. But go ahead and try it out for yourself, and then we will reconvene in just a second. Okay, so propane, a common fuel used for heating in rural areas. We want to know the number of moles of CO2 formed when 3.74 moles of propane is burned with excess oxygen. And so this is how we will start. We'll start with the number that we have, 3.74 moles of C3H8. Divide that by the number of moles in the equation and the ratio to the moles of CO2, the thing that we're looking for. We'll cross out C3H8 on both sides and multiply across. It's going to be 3.74 times 3. And that is going to give you the number of moles of CO2 that you have at the end. which ends up being 11.2 moles. So, if you are thinking of calculating the reactants, we can also use masses, right? If you think about when you put something on a scale, or like if you were to measure the amount of material in a product without counting each individual atom, which would be impossible to do, you would need to weigh it out. So most of the time, this is a scale, by the way. Most of the time, there's going to be a mass associated with this. And in order to convert from moles and mass, you're going to need to use the molar mass of each of these things, each of the things that are present. So these are the steps. First, if you're given an equation, double check that it is balanced. If it's not balanced, go ahead and balance it first thing. If you are not given an equation, you may need to write one and then balance it. You can then convert the masses of the reactants or products into moles. The mole ratio that the balance equation provides will help you convert from one to another. Once you're in moles, you can convert from one substance to another, just as we did before. And then we want to use the mole ratio to calculate the number of moles that we have. Finally, we can convert back to masses. This is called stoichiometry. So this is using balanced chemical equations to determine the masses of your products and your reactants. So, for example, let's take the oxidation of chromium. So chromium is treated with oxygen to make Cr2O3. Now, think back to what the first step is. The first step is going to be to balance the equation. And we need to know also where we're going. So we need to look at the amount of mass that's going to be produced. That's what the question is asking for, because it's asking for grams of chromium-3 oxide. And we know that we have 15 grams of solid chromium and enough oxygen for the reaction to continue. So, we'll start with 15 grams of chromium. We do know that because this is the thing that is given to us as a number present in our question. We also know that the atomic masses of chromium and oxygen are 52 and 16 from the periodic table, and so we can find out what the molar masses are of these substances. So, first, let's balance the equation. There's 2 chromiums on one side, there's 1 on the other, and so what we will do is we'll put a 2 here, but we're not going to have enough oxygen to satisfy that. If you ever don't have enough oxygen, likely you're just going to have to multiply everything by 2 and then balance the oxygen last. So I'm going to start by doing that. We already knew that there was supposed to be a 2 right there, so multiplying that by 2 will give me 4. And I can keep this the same now. Oh, sorry, no I can't. I have to multiply this by 2 as well, but now I have all even numbers to work with. 4 chromiums, that's good. The oxygen is the only thing left. So 2 times 3 oxygens, that's going to give us 6 oxygens, which means I need a 3 right here in order to have it balanced. And what do you know, that's what we have at the bottom right here. 4Cr plus 3O2 gives you 2Cr2O3. And the molar mass calculated of chromium is going to be 2 times the molar mass of chromium plus 3 times the molar mass of oxygen. And that's going to end up being 152.00 grams per mole. Now we're going to start using grams per mole quite a bit. So let's continue. We'll start with the amount that we have. We know we have 15.0 grams of chromium, the molar mass of chromium is 52.0 grams, and so we will find the number of moles of chromium. Then this will be the number of moles of chromium. We can then plug that into a new equation that will take moles of chromium. Now that we're in moles of chromium, we can use the conversion factor, which it comes directly from the equation that we wrote out, 4Cr to 2Cr2O3. And we need to cross out moles of chromium. So moles of chromium goes on the bottom to be able to be crossed out, and moles of chromium oxide goes on the top. This will give you 0.144 moles of chromium oxide. Finally, we will begin right here with our 0.144 moles of chromium oxide. We know that for every 1 mole of chromium oxide, we have 152.00 grams of chromium oxide, and this comes from the molar mass of Cr2O3. And that gives you the number of grams. And so this is the entire thing, but I'm actually going to show you how I do it as well. So let's go back to here. We know that the equation is going to be balanced like this. 4 and a 3 and a 2. Okay. So I'm going to make a long train track, and I'm going to start with what we know. We have 15.0 grams of Cr. We need to get out of grams of Cr, so we can use the atomic mass, or the molar mass, of chromium to do that. The molar mass of chromium is 52.00 grams per mole, and we want to get into moles anyway so that we can use this equation up here. So I'm going to put the 52.00 grams on the bottom so that I can cancel out grams. 52.00 grams for every 1 mole of Cr. Okay, so 52.00 on the bottom. Now, if I were to stop the equation right here, it's like doing this first step where I have just stopped and found the number of moles, but we can continue. So now that I'm in moles, I can use the ratio up here, the chromium to chromium oxide, and I can say that for every 4 moles of chromium, there are 2 moles of Cr2O3. Now, I need to find, now that I've done the conversion, I am getting closer and closer to getting the mass of chromium oxide that I need. So the last step is going to say for every 1 mole, I need to get out of moles now and into grams. For every 1 mole of chromium 2O3, I know that the molecular mass is, let me check just to be sure, 152.00 grams. And so I will just divide multiply the top, multiply the bottom, divide the top by the bottom. And you end up with this as your answer, 21.9, with the sig figs being limited by the sig figs that you started with. Okay, go ahead and try this one on your own, and then I will show you how it is done. Okay, so we have tin 2 fluoride being prepared from tin and hydrofluoric acid. The equation is already balanced. There's a good chance that if there are numbers here already, then your equation is already balanced. But you do want to check and just make sure. There's 1 tin on each side. There's 2 H's and 2 F's, so we are golden. We're good to go. And so this equation right here is going to tell you exactly how to do it. We'll start with the 55.0 grams of hydrogen fluoride that is given in the problem. So 55.0, we will divide by the molar mass of hydrofluoric acid. We'll use the equation ratio to convert hydrofluoric acid moles to tin fluoride moles, and then we'll use the molar mass again to convert back to grams. You multiply the top. This counts as a top if there's nothing underneath it, by the way. Multiply the top, divide by the bottom, and you end up with 215 grams as your answer. Okay, try this one out. Okay, so if we have this reaction here, and we want to know what the mass of H2O is to completely react with 20.0 grams of PCl3, we are going to, instead of doing our jump from the products to, or the reactants to either of the products, we're going to do a much shorter jump and just go straight from one reactant to another. This is completely allowed. We'll start with the amount of PCl3 that we have. We'll use the molar mass again to convert to moles, and then the mole ratio. I called it an equation ratio before, but that's just because I got this ratio from the equation. But once we do that, we will be able to get to moles of PCl3. We will then use the molar mass, moles of water. We will then use the molar mass of water to convert back to grams. And the answer is going to end up being 7.87. I've taken out the answer for this, and I will show it to you later, but apologies for this. The equation was incorrectly balanced. It looked like there was a missing number, so there it is again. Go ahead and give this a shot, and then we will reconvene. Okay, so we have a reaction where X represents an unknown element. It doesn't matter really what it is because, well, we'll figure out what it is momentarily. But let's take a look. So 175 grams of X is going to produce 2.43 moles of B4X3. So where do we start? Well, we have 175 grams of X, and so we'll start there. 175 grams of X. We don't know. My mistake. Okay, so what we're going to start with is, if we're given two different values, we have 175 grams and we have 2.43 moles. We want to know what element X represents. And so one way that we can do that is by finding out what its molar mass is. So let's go ahead and do that now. So if we know how many moles of B4X3 can be made, and we know how many moles, we know the mole ratio of one element or one molecule to another, we can figure out what the number of moles of X that were used are, and we can divide that by the number of we can divide the grams by the number of moles that we have. So what we'll do is we'll start with the number of moles. So that'll be 2.43 moles of B4X3. Now, we don't need to know what the molar mass of B4X3 is because we are already in moles. But we do want to use the ratio. So for every 1 B4X3 that we have, we will then convert that to 6 moles of X. Whatever our X is, we are now going to have the number of moles, and we can then divide 175 by the number of moles. That will give us 2.43 times 6 divided by 1 gives us 14.58 moles. And so we'll take 14.5, we'll take 175 grams divided by 14.58 moles. And this is going to give us 175 divided by the 14.58 gives us 12.002, which is very close to the molar mass of carbon. And so what we can say is that this is now in grams per mole. The answer to this is going to be likely carbon. And this is exactly what is done here. So 2.43, convert it to moles of X. Once you have the moles of X, you can take the grams of X that you have and divide it by the moles that you have to get the molar mass.